Hi everyone, let's continue. So in this video, in the next two videos, we will talk about how may we use some numbers to describe variability. Okay, let's start. So measures of variability is for us to describe the spread or dispersion of a set of data. Basically, that's some measurements of how dispersed a set of data is. Okay, this is especially important when two sets of data have the same center. For example, here we have two curves. Each one you can think that's some kind of approximation of a frequency polygon. So here we have two distributions. We can see that they have the same center. Or technically, you can see that they have the same mode, right? Because their mode is just here. And if you can see that they are symmetric, that also tells you that their average is here. Okay, so their mean is here, and also their median is here. So with the three measurements of central tendency, we cannot differentiate these two distributions. But obviously they are different because the blue one is more dispersed. So that means we probably need some measurements, some numbers that can help us summarize dispersion. Okay, so that's the topic in these two videos. First, we have ranges and interquartile ranges. The range of a set of data is the difference between the largest number and the smallest number. Okay, that means we can first find the maximum, and then find the minimum, and then find the difference. And this is exactly something you did when you want to draw a histogram, right? And obviously, if range is larger, we say the data set is more dispersed. Okay, so because the largest number and the smallest number, their difference becomes larger, that typically means this data set is more dispersed. And then we have interquartile range. That's something very similar to range, but it talks about the difference of the first and the third quartile. Or you can say that it's the range of the middle 50 of data. Okay? This is sometimes more useful because it excludes the effects of extreme values. Okay, so both these two measurements are quite simple and intuitive. When these are larger, we say data is more variable or more dispersed. Then we probably want to think about whether there is anything else, because even for interquartile range, basically you just use two numbers to do the calculation, or sometimes you indeed you use some order or ranks, but you did not use all the information contained in all the numbers. So how about we define something else? Let's first consider a set of population data. Okay, there are capital N numbers and the mean is mu. Intuitively, if we want to measure the dispersion, then we want to see how each number deviates from the mean. We want to find the difference between each number and the mean. If the number is larger, if the magnitude of this number is larger, that typically means this data is far from the mean. And if this kind of number is a lot, then we typically say the data set is more dispersed. So for xi, we define the deviation from the population mean as the difference between xi and the mu, or we define it as xi minus mu. If we are talking about a simple set of data, then the deviation from the sample mean would be xi minus x bar. X bar is the sample mean. So very quickly, with this example, suppose we have xi being 1, 2, 3, 4, 5, 6, 8, and 9. Then to calculate the deviation from the mean, first of course we need to calculate the mean, or sum up all of them and then divided them by 7. We get the mean as 5, and then for x1 the deviation is -4, for x2 the deviation is -3, and so on and so on. One thing you need to see is that deviation from the population mean can be negative. That means this number is smaller than the mean. Okay? But anyway, you can see the magnitude or the absolute value of that deviation measures how far xi is from mu. Okay? So that's something. And then if we want to summarize all the deviations into one single number, then the first attempt may be to find the mean deviation. Okay, we have all the deviations, we sum them up and then divided that by n. In this particular example, okay, we can try to do this. We sum them up. Obviously, we get 0. And once we do that, the mean deviation would also be 0. Okay, well, here we have a typo. This should be 5. Okay, so in this example, your mean deviation is 0. Sounds weird because that somehow tells you, in some sense, there is no deviation. But of course, that's wrong. Actually, there are deviations. Some numbers are far from mu, right? If you look at the numbers more carefully, you understand why this happens. Because the -4 cancels 4, -3 cancels 3, and so on and so on. If you think about the definition of mean again, then you somehow should be able to convince yourself that if we define mean deviation in this way, it will always be 0, right? Because mu is calculated with some concepts of average there, and you do the deviations based on that average, and then you sum them up. Eventually, the negative parts will cancel those positive parts, and you will always get 0. So that just means mean deviation is not a good idea for measuring variability, because for all kinds of data sets, you will always get 0. So this measurement would be useless. Well, so what do people do? People use 2 different ways to do the adjustments. These are the most common ways, the 2 most common ways for people to do. But of course, you can invent or design other measurements, but these 2 are more popular. One is to take every absolute values for all the deviations. And once we do this, we call it the mean absolute deviations, or abbreviate it as MAD. Okay? If you take absolute values for all the deviations and then sum them up and then take average, that's MAD. Or you can take the square for all the deviations. Then we get mean squared deviations, or we give it a special name called variance. Okay, the formula becomes you find the deviation, take square, and then take average. So in our example here, we have all the deviations, right? If we take absolute value, negative things will become positive. And then the average here is 2.29. That's our MAD. This number is our MAD. And if we take square, then -4 becomes 16, -3 becomes 9, and so on. Summing up all these numbers and divided it by 7, we get this. This is our variance, the variance of this set of data. So now we have 2 ways to measure variability of a set of data. Either you use MAD or you use variance. These are 2 measurements that use all the information contained in the data set to produce 2 summarizing numbers. And intuitively, if these two numbers are larger, then that means the data set is more dispersed. Okay, so let's think about the following example. Suppose we have two 7-student groups, and each of the group, all the students take one specific exam. For group 1 students, the exam scores are 70, 72, 75, up to 81. For group 2, it's 58, 63, blah blah, up to 97. So we have two groups of students or two groups of grades. Here, this is the first grade and the first set of grades, and the mean is 76. For the second group, the mean is also 76. Okay, so if we use mean to be the measurement of central tendency, these two sets are the same. And then if we try to calculate deviations, is here. MAD can be calculated in the fourth column, and the variance is at the last column. We can see that for the second group, the MAD is larger, and the variance is also larger, right? Then we say the second set of data is more dispersed. If we look at those original numbers again, indeed we would agree that the second group set of data is more dispersed. Or we can say that, okay, these 7 students, their scores are somewhat different in a larger degree. Or if we use grades to judge their ability in a specific area, we say they perform not so close to each other, or their performances are quite different, quite at different levels. But for group 1 students, their working abilities or their abilities are somewhat more similar to each other. Okay, so we have MAD, we have variance. In the next video, we will go deeper to the analysis of these two measurements. Thank you.